Hello, and welcome back to A Slice of Physics. In this video, we will discuss equilibrium of an extended object. In the first part of this course, when we worked with free body diagrams, we represented our particle of interest as just a particle or a dot. And then we showed all the forces acting on this object as originating on this particle representation. So they would look something like this. I might have a force acting straight down like that, a force in that direction, and a force in that direction, and so on. And in these cases, the condition of equilibrium for our object was that the net force acting on the object was zero. Or if we wanted to use the coordinate axes representation, we would say that the sum of the forces in the x direction had to be zero, and the sum of the forces in the y direction had to be zero as conditions of equilibrium for our defined axes of x and y, which in this case might be x direction like that and y direction like that. Well, more recently, we have been dealing with objects that have an extended shape where the force is represented not only by its magnitude and direction, but its position of application is also relevant. So if I have a plank that's pivoted at a point like this force acting here tends to create a rotational motion around the pivot, and we represented that as a torque, which is related to not only the magnitude and direction of the force, but also the distance of the force from the pivot. So in this video, we will discuss the conditions of equilibrium in situations like this. Let's take the example of a seesaw. So here's the plank of the seesaw, and here's the supporting point, the pivot, around which it's balanced. And let's say the seesaw weighs 20 newtons. So the force of its weight acts straight down at the center of mass right at the center as 20 newtons. And the normal force from the support acts in the upward direction, and it's also 20 newtons to balance the weight. And let's say this is a perfectly balanced seesaw. So when it's just sitting out there like that, it's horizontal when there are no other forces acting on it. Now, let's say two children named Abe and Beth come to play with the seesaw. And rather than sit on it, Abe first pushes down on this end with a force of 10 newtons. And Beth takes the other end. Instead of pushing down, she pushes up on this end with a force of 10 newtons also. And let's say the distance between the forces that Abe and Beth apply and the pivot is 2 meters each. So we got 2 meters here and another 2 meters between the pivot and Beth's end over here. Okay, let's now analyze the forces on this seesaw. So there are no forces in the x direction, so the sum of forces in the x direction is automatically zero. And by the way, here are the x and y axis in this case, our usual horizontal for x and vertical for y. And the sum of forces in the y direction, if we tally it up, we got 10 plus 20, 30 newtons acting in the upward direction, and 10 plus 20, 30 newtons acting in the downward direction. So the total of all of that ends up being zero as well. So given these two conditions, is this plank going to be in equilibrium? Well, we know from practical experience that this plank is not going to be in equilibrium. It's going to swing down on this end, and the right end is going to swing up. So the plank is going to rotate around the central pivot. Well, why is that, even though our equilibrium conditions that we have used in the past are met? That's because with the extended geometry of this object and forces applied at different points along the object, we now have to consider torque as well. And as you have learned recently, torque is the perpendicular component of the force times the distance to a pivot, or the force times the perpendicular component of the distance. So let's now consider the torque of these four forces acting on the plank around the pivot, which is right at the center point of the plank right there. So two of these forces, the weight and the normal force, pass right through the pivot. And because of that, they do not have any torque associated. The lever arm is zero. The torque from Abe's force, let's call that tau A, would be the 10 Newton force times the perpendicular distance to the pivot, which in this case is 2 meters. And since this torque is counterclockwise, that becomes a positive. Remember, clockwise torques are negative and counterclockwise torques are positive. So this gives us a torque from Abe's force of 20 Newton meters with a plus sign to indicate that it's a counterclockwise torque. And then the torque from Beth on the right side, let's call that tau B, would be the 10 Newton force also
times the 2 meter perpendicular distance between her force and the central pivot. And her force also creates a counterclockwise rotation. So once again, the torque will be positive. So this gives us another positive 20 Newton meters. And if we take the total torque on this plank, it's going to be the torque from the weight, which is 0, the torque from the normal force, which is 0, the torque from Abe's force, which is plus 20 Newton meters, and the torque from Beth's force, which is plus 20 Newton meters. That gives us a total torque of plus 40 Newton meters. And it's this net torque that's responsible for creating this rotational motion and not keeping this object in equilibrium. So for an extended object where the geometry is important and we can no longer depict our object as a particle or a dot, as we did in previous problems, we have a third condition that is required to ensure equilibrium. In addition to the x forces adding up to 0 and the y forces adding up to 0, we have to have the total torque on the object around any pivot point to be 0 as well. So these three conditions, if we ensure them, then we can say that an extended object will be in equilibrium. So let's say Abe now sits on the left end of this seesaw and his friend Beth
comes and joins him on the other end, and you will have to forgive my sketching. I'm not the best at drawing, so this will have to do. For Beth and Abe was over here, and let's say Abe's weight is 80 newtons acting in the downward direction, and let's say Beth weighs the same amount as Abe, so her weight is 80 newtons also acting over here. And as before, Abe was at a distance of 2 meters from the center of the plank, and Beth is at the same 2 meter distance at the other end. And as before, we have the weight of the plank itself, which was 20 newtons acting in the downward direction like that. So now the normal force would grow to balance the sum of these three downward forces. So the normal force from the pivot is going to be 180 newtons acting in the upward direction in order to balance the 80 plus 20, 100 plus 80, 180 acting in the downward direction. So now if we look at our coordinate system and set the x-axis like this and y-axis like this, as usual, we see that the sum of forces in the x direction is 0. That's easy because there are no forces in the x direction. And in this case, we also have sum of forces in the y direction is 0 because the normal force grew to support all the downward forces. Let's see what the torque is. So the torque, as before, from the weight of the plank and the normal force are both 0 around this pivot. The torque from Abe's weight is in a counterclockwise direction, so that would be positive. So torque Abe is a positive 80 newtons times 2 meters, which gives me plus 160 Newton meters. And the torque from Beth, let's call this tau B, is now this torque is in the clockwise direction around the pivot that we chose. So clockwise torques are negative, so this will be negative 80 newtons times 2 meters. That gives me minus 160 Newton meters. And so now if I want to do the sum of my torque, in this case, I've got the 0 from the weight of the plank, 0 from the normal force. I've got plus 160 Newton meter from Abe, minus 160 Newton meter from Beth, and that gives me a total of 0. So in this case, I have satisfied my third condition for equilibrium of the total torque being 0 around our chosen pivot. So this seesaw now will be perfectly balanced, which fits with our common sense. If we have two kids of the same weight sitting at opposite ends of a beam that was perfectly balanced to begin with, they're going to remain balanced when they're both on it. So we have seen that the conditions that we set up in physics match our common sense intuition for equilibrium of an extended object. Well, one last point I want to make here. We chose our pivot for calculating the torques at the center of the beam. Now it turns out that when the torque is 0 around one point, as long as the first two conditions of the sum of forces in the x and y direction are satisfied, showing that torque is 0 around one point implies that the torque will be 0 around any point. So I could have as easily taken Abe's end as the point of determination of the torques, in which case the torque from Abe's weight would be 0. I would have torque in the clockwise direction from the weight of the beam, and Beth's weight in a counterclockwise direction from the normal force. And if we take all those torques, the sum of those would also be 0. Or I could have worked at Beth's end, or I could have worked at a 1 meter distance from bets, and any point will do for determining torque. We will see in future examples that while any point will do for satisfying the conditions, we can be clever about choosing our point that minimizes our work. So that's a key part of solving equilibrium problems of extended objects, is picking the right point for determining the torque so that your work is minimized. And we'll see more about that in future examples. So in this video, we have seen that the conditions of establishing equilibrium of an extended object are as follows. We need to ensure that the sum of forces in the x direction is 0, the sum of forces in the y direction is 0, and the third condition that was new for an extended object is that the sum of torque around any pivot point has also to be 0. And if we ensure those three conditions, then we know that the object will be in equilibrium.